Right, so for our second talk of the morning session, it's my pleasure to welcome Eric Katz, who's going to tell us about lattice points and matroids and invariants.
Okay, I'd like to thank the organizers for inviting me, and I'd like to thank the speakers who came before me for explaining a lot of things that I couldn't figure out how to explain. So it's going to go a lot smoothly because of you. This work is very in progress, so if you ask a good question, you have a decent shot of being a co-author. All right, so I'm going to start with a question that I'm going to answer, or I'm going to try to answer, then one that I don't know how to answer yet, but this will be along the path. Okay, so the first question is, what is the Matroid analog of Ehrhart theory? And one thing you could say is the Ehrhart theory of the Matroid polytope. I want to give a different answer. And the second question is, what about invariants of Matroid subdivisions? I'm going to work my way towards that. Okay, and all right, and let's pretend like we're in the first day of class. If you're teaching Ehrhart theory, you ask right on the board, what is Ehrhart theory? Okay, and I'm going to give two complementary answers, and they both have algebraic and they both reflect different algebraic geometric perspectives. So answer one is the study of lattice points in dilates of a polytope. And that has that algebraically, geometrically corresponds to sections of ON on the projective torque variety attached to this polytope. So that's one answer. Answer two is the study of generic hypersurfaces with a given Newton polytope. These are hypersurfaces in an algebraic torus, so they're open things. And I'm going to call such a thing VF, the variety cut out by the polynomial F, and a little circle to denote the open piece. And then summing the coefficient, the exponents are indexed by lattice points of the polytope. Okay, and so what does generic mean? It means smooth on strat. It's a slightly stronger version of smooth. In the literature, it's referred to non-degenerate or Shun, which I consistently mispronounce. Okay, so if you have a lattice polytope, let's just come up with, write down the Ehrhart-theoretic invariance. So if I have a lattice polytope P, I can define the Ehrhart counting function, or the Ehrhart polynomial, and this is equal to the rank of the space of sections of OM. And here, this O1 is defined by the polytope. And then you write this in terms, you write down the Ehrhart series. And then there's the H-star polynomial. Turns out that you can get a polynomial out of this formal power series by multiplying by 1 minus t to the dimension of the polytope plus 1. And this thing has a lot of nice properties. And there's also a ring theoretic interpretation of it, where you take the cone over the polytope, meaning we stick the polytope into a lattice one dimension higher at height 1 and take the cone over it. So And then you can take the semi-group ring attached to this. Then you can take the Artinian reduction. It just means you mod out by linear parameters, enough linear parameters, and that the ranks of that will give you H star. And there's also a geometric interpretation. So H star is really closely related to the cohomology of this open hypersurface VF. All right, so what is the interesting cohomology of such a thing? So we have this hypersurface with a given polytope and an algebraic torus. And this thing is affine, it's a hypersurface. So since it's affine, it's missing half the cohomology, then by Lefschetz hyperplane, most of the cohomology, the only interesting cohomology that's in here but not in here is in middle dimension. So we can set the primitive n minus first dimensional cohomology. Here I'm using compactly supported, which is covariant, is the kernel of the push forward from the hypersurface to the algebraic torus. Okay, and this is the only interesting part. And it turns out this is captured exactly by H star. And what do I mean? I mean, why is this more than just a number? Because this has a Hodge structure, and I can write down the Hodge Deligne polynomial, or this is actually the chi-y characteristic. So it's like an Euler characteristic. And I know I checked these signs at one point, but I'd have some signs backwards. But so you're looking at the middle cohomology, and it's got a Hodge filtration. You're looking at the ranks of the associated gradients of the Hodge filtration. And then it's an old theorem of Danilov and Kubansky that this series is very nearly the H star polynomial. Maybe I want to call this, change the name of what I'm calling this. I'll say it's the Hodge-Deligne polynomial of this vector space equivalent, the Hodge filtration. And up to a shift. This guy is just the H star polynomial.
What is X?
Ooh,
Capital X. So this is
Ooh.
like.
a typo.
Okay, B of that, okay,
Yeah,
that's what that is.
This is really dumb, but you sure you want to evaluate at 1 and not a -1? I mean, I thought this was like halfway to do an early characteristic.
yeah,
And then-
this is,
And for early characteristic, I would want to evaluate a -1. But
so this is what I'm not sure about. Yeah, you might be right, because there should be some alternating sign, but the signs may be built into E.
that's what I wondered.
Yeah. Oh, gosh. All right, yeah, this is, it's correct up to a sign. Okay, and yeah, no, I very well may have messed this up. I had pi y in an earlier version of the talk. All right, well, anyway, H star inherits nice properties because it's ranks of associated gradeds. So there's positivity properties or sign properties of this. These cohomology groups it's a middle cohomology, but it's got a cup product. So there's an inner product of such a thing that reflects variations of Hodge structures by Batarev. There's an algebraic description of H-star coming from the Griffiths Jacobian ring, and so on. So this is a good thing. And I'll tell you, and I'll outline the proof of this. And we now know enough K-theory that you guys can do this on your own. So, because I'm gonna, when I pass to Matroids, I'm gonna invoke a similar proof.
You can push the board up if you want.
Oh, but yeah, I could do that. Yeah, why don't I do that? I have trouble doing things. Okay. So the idea of the proof is, let's pretend our projective torque variety is smooth. And we've got the torque boundary D. This is just the union of torque divisors, and let omega 1
Is
be,
there a torque variety V of F is, what's the,
oh, V of F is the hypersurface in the torque variety.
Okay.
So this is the ambient thing, which I called, did I call it X of delta P or P of delta P? P of delta P. And then I've got the log cotangent bundle. So these mean one forms that are allowed to have poles on the boundary, and somehow this lets you pretend that you're working on the complement of the divisors. So you're working on an algebraic torus, and then we've got two exact sequences. So we've got, I want to understand the chi-y characteristic of my hypersurface VF. I guess I'll write. So my two exact sequences for understanding the chi-y characteristic are junction and here the daggers mean I'm looking at the log cotangent bundle, but the proof of a junction goes through just as usual because of the Schöndis condition. And then you've got the ideal sheaf sequence.
You want your ambient torque variety to be smooth?
Yeah, you could fix it. Yeah, we're gonna suppose it's smooth in this case. It's easy to, it's a straightforward to extend it to not smooth.
what is a log cotangent?
So what it means is if D is a normal crossings divisor, it means your one forms are allowed to have poles along the divisor. And it also comes out of the machinery of log structure, but somehow by results of Deligne, it sort of does an inclusion exclusion that lets you just look at the interior. So it lets you pretend like you're looking at the complement of these divisors.
Sounds like it's about definers, but where does cotangent bundle come in?
Oh, because I want to compute I'm interested in, this is an Euler characteristic of I want the chi-y characteristic, so I'm gonna, to look at the cohomology, I'm gonna look at the different Hodge groups, and I extract the parts of a given p-type, and that's looking at powers, exterior powers of the cotangent bundle. But in the log setting, if I just want the interior, I do the log cotangent bundle.
Okay.
Yeah. Okay, and then, so it comes down to just computing this thing. And what you do is, so you have to do this on X rather than P. So say pretending like this actually came from from something on the ambient space, you could do the Euler characteristic on the computation on the torque variety. And so you need to have this OX, but you've got a description of OX coming from this exact sequence. And then you need a description of this bundle, and you use this of this bundle, and you use this exact sequence. And then just, it's a couple lines of K-theory computations. So it's not so bad. And I didn't say the words magic dust. Or now I did. Okay. So what can we say about properties of H star? Anyway, when all the dust settles, you're going to get powers of, you're going to be computing Euler characteristics of OP and X, but X is in the class of O1. So that's counting lattice points, and you'll get a lattice point enumerator, and all the algebra will amount to just extracting the H star polynomial from the Ehrhart series.
And that's the only place where you use that it's a torque variety.
Yeah, the only place, I use the fact that, well, yeah, that's easy to compute, and I also use the fact that torque varieties are log parallelizable. And that will actually become important later because that assumption will not be true. Okay, so, all right, so we get non-negativity of H star, non-negativity up to sign. Now, H star is not symmetric. And this gives us one way of thinking about why it's not, because we're computing the chi-y, we're computing Euler characteristics of something that's not compact. So you don't expect Poincare duality to hold, or Serre duality to hold if you're talking chi-y characteristics. But you can always close this up in the torque variety, and might not be smooth. You can pretend that it's smooth by using intersection cohomology. And then you can talk about the analog of this chi-y characteristic of the middle cohomology in this setting. And this leads to something called the local H star polynomial, which is chi-y of the middle primitive cohomology of the thing you closed up. So, and this thing is symmetric. And then you can relate this local H star polynomial to the usual H star polynomial by a fancy form of inclusion-exclusion. And I'll just write this down because I love this stuff. And I'll tell you where it enters into combinatorics. Okay, so the sum over faces of my polytope. Here you've got signs, you're doing inclusion-exclusion along H star, but the terms are weighted by the G polynomial of the post set, like an interval in the post set. And what's really happening is you're trying to do inclusion-exclusion, but there's some singularities, and this G compensates for the singularities. In the Matroid story, G is going to be 1, so it's not going to be so bad. And so anyway, the upshot of this is Poincare duality for intersection cohomology of the smooth thing corresponds to symmetry of the local H star polynomial. And then the symmetry of this of the closed thing corresponds to a property of the open thing called the septability. So you've got septability of H star, And this susceptibility is also a consequence of Ehrhart reciprocity. So it's a combinatorial reciprocity theorem is reflected in the susceptibility. And I learned this perspective from this wonderful paper of Stanley called subdivisions in local H or subdivisions in local H vectors. And it was a perspective motivated by Koshta-Lushnik theory. All right, so I want to at least state the theme that invariants come in pairs, symmetric and acceptable ones. All right, how are we all doing? Okay. It's okay, just this is fancy talk. Just think inclusion, exclusion, and you won't go wrong.
Eric, can I ask?
Yeah, please.
Is that local H-star thing, was that defined by Stanley as such, or was there a different definition that happens to match that?
I think there was a different definition because it was motivated by local H vectors, and I think people were writing down unimodular triangulations and looking at how H-star polynomials decomposed. But I don't know the story. Like, certainly Stanley deserves credit, and I want to say Athanasiadis probably also does too. Yeah.
I'm afraid I missed what acceptable means.
Acceptable means it obeys some combinatorial reciprocity theorem. So it's some property that in the incidence algebra of the post set of faces. But the idea is I could think of it as something like Poincare-Alexander duality for this open thing. So it says that you don't have symmetry, but if you took the palindrome, you could rewrite it as a sum over strata. So if you look at the definition of the H polynomial, that's what it is. Mm-hmm.
So it's not a property of a single polynomial, it's a property of all the H-star polynomial faces.
Yeah. Probably should have said that. Mm-hmm.
What is L-star?
Oh, sorry, the local H-star.
L-star is the local H.
Yeah.
What is local?
Local, it really means it's a closed invariant. It was a historical accident that was called local. I think they were thinking of stripping out the boundary when they wrote this down, but I prefer to think of it as adding the boundary.
So you're telling us that it should be, you take the Euler characteristic for this intersection homology. What's the Y? The Y is.
Because
like I was like.
So that's that variable in the E that I wrote down. So what it's doing is it's a variable indexing which part of the Hodge filtration it's coming from.
B.
And we got smaller clarification.
Yeah. Yeah. I'm gonna have to say, you can ask Alan Stapleton who taught me that he's not here. Wish he was here. Yeah, so this perspective was taken in a series of papers written with Alan, and this is just a tiny bit of those papers.
I guess if you work with polytopes or poset, how should we think about that formula?
Oh,
Yeah.
so, okay, so you should think about it as like when you construct the H polynomial of a poset. So it obeys pretty much the same formulas here, except it's souped up to do Ehrhart theory instead. I mean, I think of it as inclusion exclusion, twisted by these G terms. Okay, but fortunately, when I start talking about the Matroid story, which is new, these things are all really trivial. So you don't have to, these things won't enter in. And there's a local expert on this stuff who I can refer questions to, but he may not know he's a local expert. We'll see. Okay, so, all right, so why might I care about this? So if I have a family of hypersurfaces, that gives me a degeneration. So if F is a Laurent polynomial whose coefficients that are functions on a punctured disk, then I can view my hypersurface as a family of hypersurfaces that might degenerate over the origin. And then if I look at a generic fiber, so if I look at the primitive middle cohomology of the generic fiber, it's going to have a monodromy action from going around this punctured disk. And then there's something called the weight monodromy filtration, which is essentially the Jordan, it's essentially the Jordan block decomposition for the monodromy operator. It ends up being quasi-unipotent, so there's this Jordan block decomposition, and you look at the size of the Jordan blocks, and it's some complicated way of encoding that. But the upshot is you have a Hodge filtration. So on this cohomology, you've got Hodge, you've got weight monodromy. So the upshot is when you have this degenerating family, it gives you an even more complicated Hodge-Deligne polynomial. So you do a 3-variable invariant. But what's cool about that is that it just reflects the combinatorics of a lattice subdivision. So this is exactly what Melissa was talking about in her talk about how you get these subdivisions, so you get a regular subdivision from this data. And it turns out that this invariant reflects invariants of the subdivision. All right, it's about to get less weird. The talk's it's gonna get elementary again. So this is because I don't have the Matroid analog of this part yet. And then we'll start again with Matroids. Okay, so if I have a regular lattice subdivision of P, I can define an H-star polynomial attached to the subdivision, and it's a 2-variable invariant. And it can be written as a sum over faces. So all you need to take from this is that it's a 2-variable invariant, which tells you something about which lattice points lie in which faces. And somehow this is reassembling the H-star polynomial. This will specialize to the usual H-star polynomial. It's reassembling the H-star polynomial from the L-star polynomials of each face, together with a local term which measures how these faces intersect. So if you've thought about things like the Steenbrink spectral sequence for computing cohomology of generic fibers given a degeneration, this is somehow a combinatorial analog of it. All right. Okay, let's start again. Already on the wrong foot. Okay. Okay, so.
Is H supposed to be, wait, no.
Link.
Yeah, it's the link of the face after
Got
the
it.
subdivision S. So this is the H you'll see in EC1. Okay. All right, so I'm gonna try to do this with Matroids instead of Polytopes. Okay, so we can start again. I've already hopefully I haven't worn out my welcome yet. Okay, so instead of Polytopes, we'll have Matroids. Instead of torque varieties, we'll have wonderful compactifications. Instead of the algebraic torus, we'll have the hyperplane arrangement complement. So I guess I'm thinking about realizable matroids here given by these hyperplanes HI, and I look at their complement that corresponds to the algebraic torus. Instead of O1 on the projective torque variety, I'm going to have something called the permutahedral class. And instead of the hypersurface attached to with a given Newton polytope, I'm gonna have a hypersurface in the wonderful compactification in the linear system of the permutahedral class. So I pick a generic, this is a very ample class, so I just pick a generic section of it. Okay. So before I go to hypersurfaces, I want to tell you that you already know invariants that fit into this framework. Okay, so we know the characteristic polynomial of a matroid. It's divisible by q minus 1, 0 and q equals 1. Do this division, you get something called the reduced characteristic polynomial. And then this guy has a geometric interpretation. It's the chi y characteristic of the hyperplane arrangement complement. So the characteristic polynomial is already the cohomology of an open thing. And this is a consequence of the Orlik-Solomon theorem. And so this is an acceptable guy, and we'll be able to close it up to a symmetric guy. All right, and we'll talk about that. And I'm going to give you the geometry, and I'm going to define the wonderful compactification, all this stuff too. And so the theme of this talk is going from the characteristic polynomial, which corresponds to, well, invariants of this, to invariants of this open hypersurface inside the hyperplane arrangement complement. Okay. Okay, so let me give you the geometric setting. So we're going to suppose our matroid is realizable, and it's realized by a collection of projective hyperplanes inside of r-dimensional projective space. And the hyperplane arrangement complement is just that. And I want to write down a normal Crossings compactification of U. And what I'm going to do is I'm just going to blow everything up. So I look at all the intersections of the HIs. When they intersect down to points, I blow up those points. Now that I've blown up the points, I look at the intersection of their proper transforms. When they intersect to lines, I blow up these lines, and so on. So I'm blowing up the zero-dimensional strata, the one-dimensional strata, until I get the wonderful compactification. Okay, and I can relate this to the permutahedral torque variety. So the permutahedral torque variety is what happens when you have a uniform, what would you call it? The Boolean hyperplane arrangement, the uniform hyperplane arrangement, and start blowing that up. So if our hyperplanes are cut out by these linear forms L0 through Ln, this induces linear embedding of projective space in Pn. So here it is. sorry. The inverse images of the coordinate hyperplanes. And now what we can do is we can blow up the coordinate hyperplane arrangement in here. And that gives you the permutahedral torque variety. So when we blow things up, for both of them, it induces a map from the wonderful compactification into the wonderful compactification associated to the uniform arrangement. And this is just the permutahedral torque variety, which I'll denote by X sub E. I've got too many X's in this talk. All right. And this guy is a projective torque variety. It's coming from the permutahedron. So in particular, it's got an O1 on it. And I'm going to define the permutahedral class to be the pullback of this O1. And then I'm going to let Z will be a generic hypersurface in the wonderful compactification in the class of pi.
Maybe like the standard permutahedron, kind of like 1 through n.
Yeah, the standard one. Yeah. Ooh. And, oh yeah, and actually I had a note that ended up in the wrong place in the talk, so I need to say this now. Okay, so I said this guy, the characteristic polynomial is acceptable. So does it have a symmetric analog? Because they should come in pairs. So the symmetric thing is going to be the chi-y characteristic, which is really just the Poincare polynomial of the wonderful compactification. And this is the Hilbert polynomial of the Matroid shower. So this symmetric thing is something that we already know about, although it's kind of hard to figure out what exactly these numbers are. And the fact that these are in pairs like this was studied in detail in this very nice paper, Ferroni, Mathern, Stevens, and Vecchi. Okay, now the local expert knows who he is. All right, so sorry for drafting you. I don't even know you, but I just met you. But, oh my gosh. Oh, I'm only getting worse as I get older.
Very sure.
I think Leo has known me the longest. Okay. Okay, so let's try to write down some invariants like Ehrhart theory. Okay, so one thing to try is to write down the analog of the Ehrhart polynomial. So I call this the permutahedral polynomial. And this is very closely related to some things that were studied in Chris Ehr's thesis. So we're just counting sections of powers of the permutahedral class. So this guy is ample, so the only thing that contributes is H naught, so we're really just counting dimensions of sections. All right, so what is this? Does it depend on the realization of the matroid? And the answer is it doesn't. We can, so by work of Larson, Lee, Payne, and Proudfoot on K rings of matroids, we can combinatorialize this definition. And this turns out to be valuative. So invaluative in this case means that if I have a matroid for my matroid M, if I have a matroid subdivision of this matroid, the invariant is additive under matroid subdivisions, or Bayes inclusion exclusion under matroid subdivisions. So And this is not so hard to show. So if I were to decompose the Matroid polytope of M into smaller Matroid polytopes, this invariant obeys inclusion exclusion over the subdivision. And we can actually answer what this invariant is. Kind of cool. So this is just adapting this argument is due to the identification of this is due to Max Cutler, adapting an argument from Chris's thesis. So what we want to do is it's related to the independence numbers of the Dilworth truncation associated to this matroid. This is something I don't really get. Okay, so the rank of our matroid is R plus 1. And then there's something called the modified Dilworth truncation of this matroid. So the ground set of this guy is the set of pairs of elements of the ground set of our original matroid M. And these are subsets of the pairs, sets of pairs that obey the Dragon Hall-Rado condition. Whatever that is, I can explain literally what it is. You asked me. But then the cool thing is that if you were to look at this Predral polynomial, it's counting the number of independent sets in this modified Dilworth truncation. So in particular, these coefficients are ultra log concave by Mason's conjectures. That's pretty cool. All right, so where do we go from here? I want to enrich other invariants. And eventually I want to work my way towards something like the H-star polynomial. Okay, so how do I make an invariant permutahedral? All right, so I'm going to do K-theory. So I'm going to want to take Euler characteristics on the wonderful compactification. So if I have some K class F, I'm going to make some smart choices of K classes. I can evaluate this, I can compute this, at least theoretically, by relating it to a torque variety, because the wonderful compactification lives in the permutahedral torque variety. So say, if I pick a smart K class here, I can rewrite this so it gives me some interesting invariants. I can relate this computation to something on the permutahedral torque variety. Okay, and these are all ideas that I learned about from the best paper. That is Birgit Urs Fink Seng. All right, so let me write down some observations from this paper that let me enrich my invariants. So first I have a description of this guy, the fundamental class of the wonderful compactification. It is given by, it comes out of one of the tautological classes defined in this paper. So there's a certain K-theoretic class called QM, dual, and then I apply the Adams operation to it. An Adams operation is just a formal power series with exterior powers. And this is something well defined in K-theory. All right, and moreover, the one thing I want to insert is a log cotangent bundle, because I like those things. Oh man. How you guys doing? Yeah, good.
What do you mean by enrich?
Enrich, well, I want to take some invariant that I already have and make it incorporate data from this permutahedral world. So I want to take things like the characteristic polynomial and the Tutte polynomial of the Matroid and see if I can enrich it by incorporating this permutahedral data and maybe get something new. So I'll say some words. I'll tell you how I'm going to rephrase the things I want to enrich, and then I'll write them down. But we already have this permutahedral polynomial, which involves powers of pi. It's already something K-theoretic. So this suggests I write down characteristic and Tutte in a K-theoretic way, and then throw in powers of pi. And this is all perspective I learned from the best paper. Chris, are you happy? I can't tell.
I'm smiling.
Smiling under the mask.
Okay. Well, we'll never know. Okay, so what we also almost have a description of the log cotangent bundle of the wonderful compactification. So there's this class called SM. It's another one of the tautological classes from the best paper. And they note that it's almost the log cotangent bundle of the wonderful compactification. It just differs by a trivial bundle. All right, so, okay, so let me show you how to write down the reduced characteristic polynomial in this world. This is pretty fun, actually. I'll do this on this board. Like, I know this conference has gotten me more excited about doing K-theoretic computations and combinatorics, so I'll do one here for you guys. Okay, so look at the reduced characteristic polynomial. That's chi-y characteristic of the projective hyperplane arrangement complement. And that I can relate to an Euler characteristic on the wonderful compactification. I want to consider the interior of the wonderful compactification. So that suggests I look at the log cotangent bundle. Here, this little dagger means log. This is the Adams operation again. That corresponds to taking exterior powers of omega 1. So we're taking the terms in the de Rham complex. And now I don't want to do my Euler characteristic computation on the wonderful compactification. I want to do it on the permutahedral torque variety. Fortunately, all the interesting stuff I want is all pulled back from the permutahedral torque variety. So this works out to be the following class, and this is all noted in the best paper. Okay, so now that gives me a formula for the Euler characteristic. That gives you a formula for the characteristic polynomial as an Euler characteristic in K theory. And then I've got this -1 for QM dual, which gave me the fundamental class of the wonderful compactification. But maybe I want to loosen things up a little bit and throw in a U here and a V here to make it a two-variable thing. This now, forget about this. This just corresponds to a factor of 1 minus y. If I have this Euler characteristic, this contains the same information as Tutte. It's the Tutte polynomial up to a change of variables. And now I want to make it permutahedral. So I'm going to throw in pi. So now it's a three variable thing, u, v, and w. And here, what does it mean when I'm raising pi to some power? Just means looking at the following power series that I'm inserting. All right, so this gives me a new invariant. I call it the permutahedral Matroid invariant. It specializes to the permutahedral Tutte. And I'll write down the chain of specializations, and then I'll tell you about the
It's like one minus pi, you know, like,
one minus, what's that?
is one minus pi better, like just pi?
Yeah.
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 This is just like the normal person interpretation of what you're doing.
Yeah, of course, but right, I want to write it as a power series in one minus pi, because one minus pi corresponds to the fundamental class of a hypersurface, so. I'm gonna say the wrong thing because I'm up on the board, but that I want to think about is, you know, it'll intersect down to zero. So this makes this this makes this not a formal power series. Or it's so I can write this natural log term. This will be a polynomial, I think, in K theory. I want to say the natural log thing will be.
But it's like literally
Yeah,
W times the divisor.
Is pi a line bundle or a divisor?
pi is a line bundle. So one minus pi is a divisor. Thank you so much. Oh, God. Yeah, pi should have been, oh my gosh.
So I think, yeah, so literally the W's tensor power of that line bundle.
Yeah, that's all I'm saying. Oh, thank you. You saved me. All right. However, on the salary committee.
Nice.
What? Okay. So anyway, this thing's pretty cool. It has properties analogous to Tutte and Ehrhart polynomial. It's valuative. It satisfies a form of Ehrhart reciprocity, which is kind of cool. So I'll write down the Ehrhart reciprocity. This is kind of a mess, but okay. Just note there's a minus W in here. Here, this is a sum over flags of flats. So this is the acceptability statement. It looks hideous, but if you write it in terms of the incidence algebra, it's not so bad. So it might be acceptable then. I tried. Anyway, this is related to this reciprocity of the characteristic polynomial that was studied by Ferroni, Mathern, Stevens, and Vecchi. And so anyway, I'll take it. And it's less complicated than other acceptabilities. There aren't statements because there aren't any funny G's in here because the one with compactifications is simple normal crossings. And then it has a specialization to permutahedral Tutte just by a change of variables. It obeys Matroid duality. I have no idea what this invariant is. I don't know how to characterize it. I can write down a recursion for it, but the recursion is an absolute mess. So here's Matroid duality. I want to characterize it by writing it down for snake matroids, and I think that's a doable thing. Those are generators of the valuative group of matroids. So once I know what it is on snake matroids, I know what it is. And it has a specialization to an enrichment of the characteristic polynomial. So I can define a permutahedral characteristic polynomial. And then I also I also have the analog of an H-star polynomial. So what would the H-star polynomial do? It would look at the middle cohomology of this Z and see which cohomology didn't come from the wonderful compactification. So it'd see the primitive middle cohomology, and I'll just write down the permutahedral H-star polynomial because we're all hungry. I won't say too much more about it, but and of course, instead of writing it as a polynomial, I'm writing it as Homolar Laurent series in Y inverse. It actually is a polynomial, although you can't tell. And I was able to derive this just by recopying the Danilov-Khovansky argument. This turns out to be a polynomial. It obeys. For realizable matroids, it should have some positivity properties because you're counting the ranks of graded pieces of cohomology. It is indeed a polynomial for non-realizable things. I actually figured out the proof of this when I was making some changes to the talk this morning, but I found a difference operator that annihilates it. So it's probably pretty good. Anyways, it has susceptibility properties coming from Serre duality, which means it also has a symmetric cousin, but I don't know what it is. I would love to interpret this as ranks of a vector space, because you've got the Griffiths-Jacobian ring, which gives you middle cohomology of a hypersurface, but then you also have the Orlick-Solomon algebra, which gives you the dimensions of a hyperplane arrangement complement, and I think you can combine both of them together and find some vector space that this guy is the dimensions of. Anyway, I don't know how to compute this. It has terrible deletion contraction properties, which means it might be more interesting than another specialization of Tutte, but I'm not ruling out that it might just be another specialization of Tutte. And I'd love to I can compute this by localization, which means I can't compute it, but I'd love to tame the combinatorics of localization and maybe rewrite it as activity sum. And moreover, I think I can probably soup this up to give invariants of Matroid subdivisions.
So two quick questions regarding this thing.
Yeah.
What's the degree of this polynomial?
Ooh. It should be, I want to say it's just the rank of the Matroid.
Okay, and do you know?
Or it's maybe the rank minus, no, it's the rank minus one, it should be.
Okay, and do you know what it is for the Boolean Matroid?
You believe I don't? I really should have, that probably should have been the first thing I tried. Wait, because it's, yeah, I could probably, like, if you gave me a half hour, I could write it down. Because then you're just computing on a torque variety and it ends up being so. Right, for Boolean Matroid, then it's just the H-star polynomial of the permutahedron.
Alex, something I missed in this is why the permutahedral class as opposed to some other generalized permutahedron. In the first half, I took arbitrary line bundle.
Right, so it is the permutahedral class. It's pulled back from the permutahedral class. Oh, for the standard permutahedron.
Right. I mean, would it work if I took a different generalized permutahedron?
Oh, sure. Yeah, you could throw in a different pi. It just wouldn't be canonical. It would be another piece of data.
And it's like the top board is the reason you want to look at pi?
That I've got an answer. Yeah, but also like your torque, if you have a polynomial, a polytope,
right?
You have a canonical O1. Maybe I want to say if you've got a matroid, I just want to have
I don't know. Could you?
I want to. Yeah, you
games or whatever. Even the pi argument as well.
Yeah, no, that's a great idea actually, because Postnikov, right, wrote down, like, he varied the lengths which corresponded to changing this generalized permutahedron, and I think he wrote down some differential equations that maybe I could use to compute. That's a great idea.
But your ambient isn't smooth, you use a different guy.
What's that?
If you're looking at the, like, in the stuff you did over there, you're looking at the wonderful variety, and it's like important,
Oh.
it's ample.
Yeah,
Otherwise, you have to look at the image of the wonderful variety, which would be.
yeah. Yeah, but I could maybe make a generic choice of pi and look at limits of it. I mean, I like that pi, but I think combinatorially, it might make a lot of sense to loosen it up, as Alex says. You want to be co-author?
We'll talk.
Okay, awesome.
Other questions? If not, let's break for lunch. Let's thank everybody.